Yeah, my name is Atsuya Hasegawa, and I'm a postdoc at Nagoya University. And yeah, today I'm telling you about fine-grained complexity of the local Hamiltonian problem. And yeah, from size-preserving circuit-Hamiltonian construction. This is based on joint work with Naifui, François, and Yuchi. And yeah, I'm going to include very general introduction. So please, yeah, feel free to interrupt if you have any question. So okay, so let's get started with the origin of complexity theory. And Cook and Levin independently discovers that any proof verification procedure can be embedded into the constraint substructure problem, or just simply SETH. And thanks to the Cook-Levin theorem, we know SETH is NP-complete. And subsequently, Richard Karp discovers that there are many natural NP hard problems by the Karp reduction. And yeah, as you know, these discoveries are the foundation of theory of computation. And quantum analog was shown by Kitaev, following the idea by Feynman. And Kitaev showed any quantum proof verification procedure can be embedded into the local Hamiltonian problem, which is quantum generalization of SETH. And so why is the circuit Hamiltonian construction important? And yeah, so the Cook-Levin theorem is the heart of TCS, and estimating the ground state energy of quantum medieval system is one of the most important computational tasks in quantum physics. So the circuit Hamiltonian construction really connects the two fields, and that's why it's important for, especially for quantum information processing. Okay, so from now on, I'm going to review what's the local Hamiltonian problem and the Kitaev's construction. And okay, so okay, so an input for the local Hamiltonian problem is some efficient classical description of the local Hamiltonian, which is a sum of local Hermitian operators. And yeah, local means each term acts on some ideally constant number of qubits. And importantly, there is a promise gap between on the minimum eigenvalue or ground state energy of the Hamiltonian. And the computational task is to distinguish the two cases. And Kitaev first shows 5 local Hamiltonian problem is QMA-complete. Okay, so to prove it, the important idea is the concept of history state, which is proposed by Feynman. So Feynman considers that each uniform superposition of each computational step of the verification circuit. And yeah, by introducing the clock register, each computational step of the verification circuit can be orthogonal. And by considering this propagation term, we can see that the history state is a ground state for this propagation term. And Kitaev, yeah, this is the final this is the local Hamiltonian problem Kitaev considered, and which is the Hamiltonian is sum of the H in and the propagation term and H out. And H in gives some energy penalty for invalid initial state. And so it's H out gives some energy penalty for invalid output state. So rejecting output state. And yeah, Kitaev shows that for yes instance, the history state is the ground state energy for the Hamiltonian. And for no instance, the ground state energy is higher than the yes instance threshold. And yeah, this implies there exists a promise gap between yes instance and no instance. And okay, so in the previous slide, we implicitly assume that the clock representation is binary rather than unary. Okay, binary. And when we add 1 to 0, 1, 1, 1, 1, we have 1, 0, 0, 0, 0. And which means the locality of the Hamiltonian is log t. And t is the number of gates for the verification circuit, and which is usually some poly n. So the locality as grows as usually polylog n. And for when we want to consider physical Hamiltonian, we want to consider constant local Hamiltonian. And yeah, to prove the hardness of constant local Hamiltonian, Kitaev considers the unary representation of the time. And in the unary representation, t is represented as 1t. And Kitaev also introduced this H clock term, which gives some energy penalty for invalid time binary. And thanks to the unary representation, we can make the propagation term very local. Say it's ut is usually 2 local, and this time forwarding operator is 3 local. And Kitaev finally shows that there exists a promise gap for this 5 local Hamiltonian. And yes, okay, this is the Kitaev's construction. And subsequently, Kempe and Legge shows that 3 local Hamiltonian is QMA-complete. And yeah, the modification is relatively simple. And finally, Kempe, Kitaev, Legge in 2004 shows that 2 local Hamiltonian problem is QMA-complete. And yeah, 1 local Hamiltonian problem is in P. So yeah, that's why this is a very canonical result. And yeah, so okay, so yeah, in fact, they introduced 2 constructions. And one is by the perturbation gadget, which is so the perturbation theory is, in my understanding, well-known theory in quantum physics, and yeah, they apply it for Hamiltonian complexity. And they also introduce some explicit construction on the binary, on the unary clock. And yeah, this is the explicit construction. And basically, so they introduce some special 2 local terms for SETH gate. And yeah, And the CZ gate plus 1 qubit unitary is universal. So we can only consider one local unitary in the propagation term. And earlier than that, Kempe and Regev reduce the locality of this forward back for time moving operators. So indeed, the whole local Hamiltonian is a 2 log. And yeah. Okay, so far we have reviewed the known construction, and from now on, I'm getting into our construction. Okay. Okay. So, and yeah. So as we've seen, there are two canonical clock constructions. One is binary, and the other is unary. And there's a kind of trade-off for the locality and size. With binary clock, we have very small size overhead. So here, size overhead is the size of clock list. But the locality grows as log t. And using unary clock, we have very good locality, but the size overhead is huge, linear in t. And our motivation is from fine-grained complexity. I will revisit soon. And we ask if it's possible to reduce a circuit to constant local Hamiltonian whose size overhead is sublinear in t. And yeah, both canonical clock construction do not meet our criteria, and we show the first size preserving circuit construction, and the answer is yes. And yeah, this is our main result. And so we show that any we show that any verification circuit we can reduce any verification circuit to d plus 1 local Hamiltonian whose size overhead is t to the 1 over d. So when d is equal to 1, the parameter is the same as the unary construction. And yeah, our result is non-trivial when d is larger than 1. And yeah, in other words, our result can be viewed as a generalization of the Kempe-Kitaev Regev construction. Yeah. So for example, when d is equal to 2, the size overhead is square root t, which is better than the unary construction. Okay, so from now,
sorry, can I quickly ask a small question? Do we have any kind of lower bounds as well on what any non-trivial lower bounds on what either the size, like maybe the product of size and locality or something like this? Do we have any indication of how close we are to optimal?
Yeah, that's a very good question. And yeah, it was, yeah, it was shown by, yeah, in some unpublished results by, yeah, some research. But yeah.
Sorry, could you say it again? I didn't catch that.
So so ideally we want to reduce circuit into, say, 2 local Hamiltonian whose size overhead is low. But yeah, I had some research proves that it was under mild assumption. Yeah. So
Thank you.
yeah, it's still unpublished. So yeah, but yeah, and yeah, but yeah, I think their results very interesting. Yeah, so yeah, our work gave us a new upper bound size and locality trade-off, and yeah, it would be, in general, it would be very nice if you have a lower bound for the trade-off. Okay, so from now I'm telling you our technique for how to get our result. So basically, we want to compress clock register, and for the purpose we use this Johnson graph, which was in So Johnson graph clock was introduced by earlier work, Chia et al. Around 2022 or 3, and so in ND Johnson graph, so vertices are the element subset of n vertices, and the two vertices are adjacent when they share d-1 element, same element. And in the ND Johnson graph, there are n choose d vertices. So, and yeah, the good point is we have very local operator to move vertices. So we could have very nice clock from the Johnson graph. And yeah, so this is one of the example of Johnson graph, 5D Johnson graph, 5-2 Johnson graph, and yeah, two vertices are adjacent if JC are one red vertices in the same position. And yeah, this is an example of the Johnson graph based clock. And okay, so in general, we can take a Hamiltonian path inside Johnson graph. And yeah, and the time of the clock corresponds to vertices on the Hamiltonian path of Johnson graph. And yeah, in this example, we can specify time by 2 local operators and move forward and backward time with 3 local operators. And so in this example, we can represent 10 time on 5 bits clock with some 2 or 3 local operators.
I'm just sorry, could you say again what the Hamiltonian path is?
Hamiltonian path is path on a graph, and each one each vertex should appear once in the path.
Yes. Right. Got it. Okay, thanks.
And connected.
Yeah. Sorry, I'd forgotten. Yeah, I read it at some point, but haven't used it, so I forgot. Okay,
yeah. So one interesting point is you use the same word, Hamiltonian, but it's different from physical Hamiltonian. Yeah. So in this figure, this circle is a simple Hamiltonian path. Okay. So in our work, we formally introduce local D plus one or D local operators to pause and forward and backward time on the ND clock. And we also introduce H clock operators, which give some energy penalty for invalid clock state for the ND clock. And then we finally combine our clock construction and the Kitaev Kitaev construction. And we have a reduction from circuit to a D plus 2 local Hamiltonian acts on large N plus order N to the 1 over D. And in our main theorem, we claim D plus 1 local Hamiltonian. So we need a further idea. And this is a bit complicated, but we combine ND clock plus unary clock. And and then for the unary clock, we can move. Okay, so this is an example of N1 clock plus unary clock. N1 clock is just single one clock, and we can forward time on the unary clock. That's okay. So blue one is a unary clock, and red one is N1 clock. And the good point is we can forward time on the unary clock by one local operator, basically. And we can pause the time on the N1 clock with one local operator. So the locality of you forward this time can be done with two local operators. Anyway, so by combining the unary clock, we can reduce further the locality of operators, and we finally have D plus 1 local Hamiltonian. The size overhead is D to the 1 over D. And there are many conditions and terms, and to have this, to claim this result, we need to do very careful analysis of the whole Hamiltonian. Okay, so next, I'm going to tell you fine-grained complexity. Okay, so which is our original motivation to investigate size-preserving circuit challenges. So, okay, so suppose that one problem have a very efficient algorithm, linear time algorithm, and another problem has n to the 100 time algorithm. And by definition, both problems are in P. But for actual problem, for concrete problems, the actual running time by program can be totally different. And for NP-hard problem, under the assumption that P is different from NP, there's no polynomial time algorithm. However, there could exist fast or exponential or even sub-exponential time algorithm. And the motivation of the fine-grained complexity is literally a characterized problem in a more fine-grained way. And for NP-hard problem, fine-grained complexity of QSETH has been intensively studied. For example, for 3SAT, we have faster exponential time. For small QSETH, we have faster exponential time algorithm. The famous one is called Schrodinger's algorithm, which is based on random walk arguments. And if K is small, we have faster exponential time algorithm, and the current fastest one is like this. And and ETH or exponential time hypothesis is a conjecture that no sub-exponential time algorithm for 3SAT. We could improve this number, but no sub-exponential time algorithm. That's the conjecture. And SETH is or strong ETH is a conjecture that 2 to the n time algorithm is optimal for large cases. So we can increase the number of this constant k, and SETH says with very large k, 2 to the n time is optimal. Algorithm is optimal. And 2 to the n time algorithm is very trivial, right? We can just touch all the assignment. And recently, a quantum analog of SETH, QSETH, was proposed. And they say we can have the global speed up, but which is the speed up is also optimal. With very large k. That's the conjecture. And okay, so as I said, the local Hamiltonian problem is QMA hard. So basically no polynomial time algorithm and standard assumption. And on the other hand, there are many studies on exponential time algorithm for the local Hamiltonian problem. And the famous one is called Lange's method, which is basically using some power method. And their running time are basically 2 to the n time, classically. And 2 to the n over 2 time quantumly with global argument. And the natural question is, we have faster exponential time algorithm for the local Hamiltonian. And okay, so assume SETH is true, and then the SETH hardness of the k local Hamiltonian problem with large k is trivial. because QSETH is a generalization of K local Hamiltonian problem is a generalization of QSETH. And to have a non-trivial result or better results, our strategy is to use Circuit-to-Hamiltonian construction to embed QSETH into some small constant local Hamiltonian. However, there are some issues. Okay? So suppose that we succeed to embed QSETH on any variable into 3 local Hamiltonian problem on 2n qubit. Then square root 2 to the n or 2 to the n over 2 time algorithm for the 3 local Hamiltonian problem implies 2 to the n time algorithm for QSETH from this size overhead. And the lower bound would be weak. And to have a tight lower bound, or you claim 2 to the n time algorithm is optimal for the 3 local Hamiltonian problem, we want really size preserving reduction. And yeah, so to use the Circuit-to-Hamiltonian construction, we first construct an efficient verification circuit for QSETH. And yeah, some property called the specification lemma is known, and test hardness hold with linear number of clauses. And then we can construct some very efficient quantum circuit to verify such QSETH. Is quantum circuit of QSETH with linear number of clauses. And then we apply our size preserving Circuit-to-Hamiltonian construction for this verification circuit. And then we have indeed a size preserving reduction from QSETH to especially 3 local Hamiltonian problem for when we apply D is equal to 2. And by this method, we can show that the SETH hardness of the 3 local Hamiltonian problem. In words, 2 to the n time is optimal for the 3 local Hamiltonian. Okay, so let me summarize.
Sorry, could you say again? Sorry, you briefly mentioned that it's important to preserve the number of qubits. I couldn't see where that that was being used, like where that was a necessity.
Sorry, what's your question?
So you said that the number of qubits have to be preserved in the preserved as in like you care about the number of qubits. I couldn't see why this was becoming crucial. I think I missed one step somewhere. Could you explain?
Maybe this step. So suppose that we have 2 to the square root 2 to the n time algorithm for say 3 local Hamiltonian problem.
Okay.
So n is number of qubits.
Oh, n is the number of qubits. Okay. I thought it was like related to the problem instance somehow. Okay.
Yeah,
it's QSETH. Oh, you're encoding QSETH into 2n qubits. Okay, so wait, isn't the n related to the SAT instance itself? No. Is n the problem size or the number of qubits? As I'm getting a bit confused. In the sense that is n the number of variables in the SAT problem? No.
Yeah, number of variable in the local Hamiltonian problem is number of qubits.
Okay. Right. Okay. And you were saying that. Okay.
So
Okay.
yeah, so we can replace n by 2n here, which implies 2 to the n time algorithm
Right.
for QSETH.
Right. Okay.
Yeah, so that's why size of height is very crucial. Investigate fine-grained complexity.
Right. And the previous result that you, the one that you mentioned earlier, where you were trading the locality and the size. So over there, size was also the number of qubits.
Yes. Basically, size is number of qubits.
As well, right?
Local, the total local Hamiltonian action.
Right. So did you have to use this result to obtain the one later, or is that a separate result? You did, right? Okay. This is just checking. Yeah. Compiling correctly. Okay.
No. I'm very happy to
Okay.
address this question. So finally we apply E is equal to 2.
I see. Okay.
And then we have square root D size of a head. And here the size is almost linear in quasi-linear in.
Right.
So that's why D equals 2. For more general case, we could need a more large D.
I see.
But for the verification of QSETH, thanks to the sparsification lemma, the gate complexity of the verification circuit is very small.
Yes. And could you also explain the specification lemma? I think I kind of, like you mentioned it quickly, I couldn't follow what was meant here. Is it important? I mean, you can skip it if it's not important, but I was just curious.
Yeah, so here we rely on the property that the number of clauses is linear. Especially
so in the lemma they show that even if it is not linear and you assume the extended ETH, then you can reduce it to.
Yeah. They show that. Yeah, they show that. QSETH with very large, many clauses can be decomposed into small clause size QSETH with some exponential time. And SETH hardness. When we claim SETH hardness, QSETH with linear terms is enough. And thanks to this property, we have very efficient quantum circuit for QSETH. And then we can apply our size preserving Circuit-to-Hamiltonian construction with these equal to 2.
Okay.
And then we can claim 3 so-called Hamiltonian problems. SETH.
Got it. Thank you.
Okay, thanks. Okay, so let me summarize my talk. So originally, Richard Feynman introduced the concept of the history state and clock register, and many even physical local Hamiltonian are known to be QMA hard. And most of them involves with size of a head. And of course, from the definition of QMA, size of a head is bounded by polynomial, but generally some large polynomial. And with some motivation from fine-grained complexity, we ask how much large size of a head do we really need for valid Circuit-to-Hamiltonian construction? And in our work, we show the first size-preserving circuit-to-Hamiltonian interaction. And we also show that SETH and QSETH hardness of the 3 local Hamiltonian. And okay, so for 3SAT, we have faster exponential time algorithm. And one could try to have a size-preserving reduction from KSAT to 3SAT. So here K is very large K. So here, and the reduction here is classical reduction. And since we have faster exponential time algorithm for 3SAT, and under SETH, there's no faster exponential time algorithm, KSAT, it is morally impossible in the classical reduction to have the size-preserving reduction property. But we show that in the quantum reduction, it is possible because we can exploit the power of Hilbert space and superposition. So we can embed more information on a smaller size in the smaller size of quantum system. And in the classical system, it is morally impossible. So yeah, so our results highlight some essential difference between the classical and quantum calculus. So, yeah, this is the most interesting point of our work. And yeah, I think, yeah, there are many open questions left by our work. And for NP-hard problem, its fine-grained complexity has been intensively studied. But for QMA-hard problem, there was almost no work for our work. And yeah, our work could be regarded as a starting point to study the direction. And an obvious open question is to ask if we can have a size-preserving reduction to 2 local Hamiltonian problem. That's 3, and even for geometry local and more specific power return Hamiltonian from KSAT. And yeah, if this is impossible, we could have faster exponential time algorithms for them. And yeah, I feel it would be very interesting. If to be really great if we could have faster exponential time algorithm for QMA hard. And yeah, more generally, I hope through this direction, we can have better understanding of quantum many-body system. And yeah, the end of my talk. Thank you very much for your attention.